Okay, so this is the webinar on the SaaS level where we are presenting ASCETiC results project. It's part of a larger series of webinar. This one will focus on tools for modeling, packaging, and experimenting with application on an ASCETiC on a cloud that runs the ASCETiC framework. Let me just recap a few of the webinars that happened in the past that will also be available from the project website's URL communicated after the fact. So here what we are seeing is that the data centers, from the graphs on the left side, that data centers are and total cloud is consuming more and more, with projections growing and growing between 2007 and 2020. And since more and more users are relying and using clouds, either hosting providers where they can just go and put their hardware, as well as community clouds, private clouds, we see that it's becoming very important that we start caring about energy. At the same time, the notion of clouds often creates a distance between users and even SaaS application providers who deploy in community clouds, and being responsible for the energy consumed by using applications or even operating applications. So on the other hand, what we see in the rest of life, in all spans of life, people are more and more caring about energy consumptions, not wasting energy, and the premise of the ASCETiC project is that software application provider, as well as people operating data centers, are no different than the rest of the world, and if given the appropriate tools, they'll do the best they can to actually operate software to minimize energy consumptions so as not to waste energy. However, they'll do that in sensible and economical, sensible ways. It won't necessarily go against their business interests. So if they have to find important where to set the trade-offs between consuming energy, providing good quality services to users and end users. To address this, the ASCETiC project then proposed an architecture on 3 layers, which is proposed on the other part of the graph, on the right side part of the graph, where we have at the bottom we have the IaaS layer, which was presented in a previous webinar. The PaaS layer in the middle, which provides the PaaS services, especially related to negotiation for selecting IaaS, for deploying applications at these IaaS, negotiating with the IaaS, and also launching and performing some self-adaptation so that the application operates in the most energy efficient way, while also satisfying user demands in terms of time performance. In the context of ASCETiC, we performed 2 industry pilot use cases. One was GPF, where they deployed an application for designing buildings and doing large-scale simulations, which was computing intensive. And then the other company, ATC, provided a multimedia cross-channel solution, as they call it. It's to handle news and publishing news, and editing and publishing news by news agencies and by consumers of news on the web. So these 2 use cases could use the ASCETiC toolbox, and we've used that to validate. The ASCETiC consortium that provided all of this is composed of the set of actors whose logos is there right below. In the context of this webinar, we will mostly use the case of the ATC news item. So let me again now say what at the SaaS level, what was expected from the IaaS and PaaS level from cloud providers, and in a sense that was covered also in the previous webinar, but let me just summarize. So the important part was that the ASCETiC framework should be able to report on data, on measurement data, on energy and power consumed, in addition, of course, to next to the cost the aspects. That was also another very important aspect, and clearly that's in the second point, where clearly if we want development teams to care well and act on this, the providers should definitely define energy-oriented price models, so that if you do an effort as a developer to try to reduce your footprint, then you should see your bill decrease, hopefully. Then also other aspects that were very important are that the ASCETiC framework and the IaaS and PaaS should help software developer in implementing self-adaptation as part of their application, in particular when it concerns horizontal vertical elasticity, scaling up or down, we could say. And of course, before you can even operate any kind of self-adaptation, the PaaS layer should help the development, the application provider select or eventually even at some point switch from one IaaS provider to another if, for instance, one cannot keep on satisfying and keep breaking SLAs. On the other hand, what are SaaS development team willing to do to help out? So clearly they are willing to keep implementing and using good software engineering approaches where they program application in modular, more and more modular ways. So, you know, in good principle of software engineering, we often find that it's important to separate the presentation from the layers of presentation, business, and data. Additionally, there is more and more a move to implementing functionality as separate little silos, and sometimes we even call those microservices. So this can actually also help propose application in modular ways where you can integrate or compose several services into an application, and each of these services can stand on its own. So clearly, developers are willing to keep on implementing properly. They're also willing to provide workloads, test scripts that perform workloads. Good practices is that such tests already exist in various type of stress test suite. Well, they're willing to kind of look at those, reshape them, and use them to actually go and take application for spins and drive workloads on them. And that's part of the third bullet, where in order to better understand how energy is consumed in the cloud, they're willing to also perform some experimentations where they will try out maybe a few deployments to figure out which one might yield a configuration, an application configurations, which is in the ballpark of what could be optimal, and then the self-adaptation would then play around that. So concretely, in the use case covered later on and in the demo presented later on, some of the questions we had to handle here with ATC were, how can we help go from an application which is a typical client-server application, where we actually have a fat client operating on a cloud, on a server, and where normally you have typical requirements such as my application should, for instance, perform a search, and the result should be presented to the user in 2 seconds or less. And now we are in this old model where this was sold as a CapEx, so it is a software product that is sold and people are making money on license, and the energy cost is actually often for the customer who is operating the solution in his own premise. And now we're moving to the cloud, so we need to be able to switch from these global requirement that happens globally for the application to where now we want to actually at least be able to measure what happens on the server side in terms of duration and in terms of energy performance, because this is something that is not so easy to see anymore. And also we need to also help people understand how to handle the operational costs, which is now we're going from the CapEx to an OpEx model where people are paying monthly membership eventually, or it might be more or less. It could sometimes be very short-lived. It could even be daily, or it could be depends on the software. But in any case, in this OpEx model, people are willing to use a service up until they decide it's not up to their expectation anymore, and they can easily drop it, not losing much money. So it's important to to help these people understand how much the operational costs of operating an application in the cloud will have in terms of cost, so that they can charge the service and make revenues out of it. And clearly, if they decide to operate if a SaaS provider decides to operate this in his own private cloud for a bunch of his customers, then clearly the energy consumptions will be part of the operational costs, since the SaaS provider will be paying the bill. So here, how did we look at answering these questions into two scenarios? The first one is we say that it will help mostly the designer and the developer, which will perform some development or test time experimentation. In that context, they might try out to deploy different rigid deployment. When I say rigid, it means that they're not self-adaptive at this point, and they try different application configurations where some of the software components are deployed on the same or different VMs to see the impact that and then they drive workloads on them, and they see the impact of these different configurations on runtime, on energy consumptions, and eventually they can also estimate the cost that it would have to operate these VMs, either in their premise or even in a community cloud that runs the ASCETiC framework. Once they've decided that maybe one of the rigid deployment seems to perform better than the others, then they will take it and they will transform it into a self-adaptive one, where, for instance, they will be able to specify some scaling rules, when to spawn new servers, when to kill some servers, to try to maintain response time, while keeping the cost and the energy as minimal as possible. And that's the second scenario, where we can specify some SLA condition and some adaptation rules and deploy them as part of the whole application. Now I will go ahead and cover the various tools that were at the SaaS level. I will be restating this later on, but we are assuming that now we have below here some IIS provider and PaaS provider who are operating the ASCETiC framework for their layers, and that we can deploy our applications who have been packaged to work on these layers. We will cover the tools here. The red dots presents the tools that I will be covering. One important part is another SaaS webinar already covered the programming model approach, where SaaS developer once they conform to the programming model, then they can specify high-level energy bounds and costs and duration bounds, and then it is the the programming model runtime that will then handle this with the IIS and the PaaS layer to maintain these bounds. In this context, the programmer just somehow delegate to the programming model the self-adaptation part. In some other contexts, it's not always possible for software designers and developers to move to this programming model. So we've provided the set of tools that will be covered in this seminar here by the red bullets 1, 2, 3, and the VM image constructor below that is also used in this context. So what I will go ahead now is go through through each of these tools and tell you, well, first off the general requirements and then how they can be installed, and then we'll move on to the demo. So globally here, for the SaaS tools that we'll be covering, here are the list of build and runtime dependency that we must have. Clearly, we need to have some Java, some Maven, some IDEs, and some of the projects are Eclipse plugin that can operate as Eclipse plugin of their own, but some others are projects or plugins that rely on some of these other tools, notably Papyrus and Axeleo. Next to that, we also rely to at some point, the PaaS layer keeps on measuring information of an application that is operating on an ASCETiC cloud, but at some point the PaaS is not meant to keep these data forever. So if SaaS developer wants to persist that data for a longer period of time, we have the experiment manager, which will retrieve all the data from the PaaS and store them in a MongoDB, which is wrapped in the SaaS knowledge base, as we've called it. So clearly, beside these runtime dependencies, we also rely on the fact that, as I said, that we need to have a SaaS, an IIS, and a PaaS ASCETiC providers available to get the whole framework working here. So now I'll just go down the list, and here won't necessarily go through running this, but it's fairly straightforward. All of these tools are available in the Git repository here. So just by cloning this locally, anyone can then follow these steps and to either, for instance, in this case, this is really a Papyrus project, which is a UML profile, so it augments a standard UML with additional aspects that are important to capture when someone models software, so that we can capture information that we can pass on from the SaaS level to the PaaS and IIS. So these profile facilitate capturing for users to specify all these ASCETiC information, and I will cover that in the rest of the webinar. This is probably the most weird tool here that has not been, it's just packaged as a standard Eclipse Papyrus profile project. The other ones are more standard projects, and we have an Axeleo Eclipse plugin, which will traverse augmented UML model and generate some XML files. And this one is a standard Eclipse plugin. To install it, just copy the jars into the drop-ins directory of Eclipse, and relaunch Eclipse, and there will be available. The way this plugin is available is by clicking on some model file, and I will show the demo later on, so no need to spend too long time on this. Another important part of the project is, once we've processed this UML, now we have an initial XML that needs to be converted into a more suitable OVF to be that will help construct and package all the VMs and deploy these VMs on the ASCETiC cloud. And also this is provided as an Eclipse plugin. It's also can be it exists in a jar form. Of course, all of these also have the source code available because they're all open source tool, by the way, so I forgot to mention this earlier. So either the source version can be taken and compiled, or we've also provided the binary version of the jar files that can each time be imported as the Eclipse plugin. And as a result of installing this plugin, the Eclipse will have a top menu called ASCETiC, in which we will see the application packages submenu there. And I will also demonstrate this in a second. Now, probably the most complex one of these series is this experimentation manager. It is actually made of several components. One of them is the experiment runner, which actually will connect. So it assumes that one or several application deployments have been deployed in an ASCETiC cloud, that the SaaS development team during their test phase has taken the workloads and exercised them on these various deployments, and that all these measurements are now done and available at the PaaS layer. And so the experiment runner, what it will do is retrieve all these measurements and import them in the SaaS knowledge base, which is the second point. And then once they're in the SaaS knowledge base, they can be visualized through the experiment measurement visualization dashboard tool. I will mention them each at a time because they are in slightly different shapes. So the first experiment manager component, the runner, is an Eclipse. It's provided in two shapes here. I'm showing the Eclipse version, the Eclipse plugin version here, but it is also available as a Maven mojo. So if people wants to have the step of connecting to the PaaS during their nightly build, for instance, and retrieving all the measurements, they can do that through some Maven as well. Again, this is a typical Eclipse plugin, and it can be available once loaded in Eclipse. The next one, which is the application knowledge base, is a Node.js bunch of web services on the top of a MongoDB. So when the experiment runner retrieves all these measurements, it pushes them in this MongoDB, and what we have is the SaaS knowledge base is the one that kind of has the Node.js API to actually structure whatever goes in this MongoDB, and also helps the visualization tools after that query and retrieves information. So this of course requires that we install Mongo and Node.js, that Node.js be that MongoDB be started, and then after that it's a fairly straightforward procedure where the in the directories above where we have the experiment manager target, we will find this SaaS knowledge base REST server zip that needs to be unzipped, and then we can just do the installation of this Node.js backend. For it to work properly, we need to edit the .js file, where we need to just make sure that we point the Node.js web service to the proper MongoDB. Here in this case, for instance, you could just have it, if your MongoDB is on localhost where you also install a Node.js application, you can just point it to localhost, but it can be anywhere. So it's free for the users to install wherever. And then once this is all done, we can just launch the Node.js and export it on a particular port. Here I say 5,000. Actually, in my example later, I'm using 8080 also. And after using these steps, the SaaS knowledge base being really a backend component is just there ready to be used. Finally, the experiment dashboard, measurement analysis and visualization tool is a JavaScript application which also interacts with this Node.js. It can be unzipped also, and the simplest way it's been packaged so that if people don't want to play with the source code, it can just be unzipped and we just open the index HTML. I mean, it's a typical web application project where with a www subdirectory that can be either opened directly wherever it's been unzipped, or it can be pushed into a web server if someone wants, if an organizations want to push it there and make it available more broadly to all the employees, for instance. Once it's installed, then we can go to the URL, but again, I will show this in a second, so I won't necessarily go that much in details of the usage, because we will just see it here. So now that I've covered all the installation part, let me go ahead and move on to the demo, where we will be using the industry use case done in ASCETiC on the ATC use case, which was a news assets software. So this software is allows the users to create news items, search for news items in the repository, and publish new news items and make them available to the public. So this is fairly data intensive, rather than computing. There is not that much computing needed, but there's large amounts of data to handle. It is based on .NET Windows technology, which is using a fat client. When I say a fat client, which means at the moment the client is not a web browser JavaScript typical web application. It is really a Windows fat client that opens up and connects through a remote methods invocation through a backend server, which performs some business logic of sorting out and storing all of the news item data. It is nonetheless, this business server could be made and pushed in the virtual environment and then be operated in the cloud. So this is what we tried to do. So that news asset, well, ATC rather, could deploy news asset in a SaaS mode, so software as a service mode, and their goal is to be able to now attract more smaller and medium-sized agencies who could not afford the current model of purchasing a product, which turned out to be too expensive, in particular if they needed to also purchase the hardware with large storage capabilities. See, by operating news asset in SaaS mode, then ATC hopes that they can provide lower costs, monthly basis costs, to these smaller and medium-sized agencies. What was not clear in their mind, and I would say even now it is still up for a final decision, is where they will operate this news asset SaaS in SaaS mode. Will it operate in ATC's private cloud and then their customer will connect to that, or will they operate it in a community cloud such as Amazon or a local Greek community host cloud provider? So in order to see how this could be handled, we are here faced with a typical web application, three-tier web applications, where we have indeed the presentation layer a business layer, which is the news asset server, and then below we have the data layer, which is provided by an Oracle database, which only gather textual information, and for the blob, or rather the videos, the audios, the images, there is it is handled by a file server on the side, which maintains links with the Oracle through some URIs that is generated internally by the business logic level. So here the idea was, could we go from this mode to a multi-tenant mode, and what would be the impact if we keep it multi-tenant, if we don't? And that's something that we will explore in the demo and see. So in the demo step, I will have a first demo. So what I will show in the first step of the demo is what I had called initially the rigid deployments, and I will really quickly go through this, and I will actually even skip these two bullet points, just mention them because I will cover them in more details in the second side of the demo. And so here I will just point out some very high-level step on these rigid deployments that we're trying out, and then I will directly jump to the experiment analyzer, the visualization tools, where we can view some of the data. Okay, so what I will assume is that in between these various deployments have been deployed in the ASCETiC cloud, that the ATC team has driven and exercised the workloads on each of these deployments. So this is assumed, and we've also imagined that the experiment manager, especially the runner, has retrieved all the information and stored it in the SaaS knowledge base. The point is that these two steps and also the manual step of exercising the workload does take some time, so that's why we're skipping them, and we cannot just actually show them as part of the demo either. So now let me go to the demo where I will jump to show you those rigid deployments. So these rigid deployments will be in the Eclipse plugin, where I will. So I've already modeled them, so that we do not waste a lot of time here, but let me just close everything and we will just see here. So this is a typical Papyrus project here, where we in the end have a model file where we can do different things. In the context of this, we have, now if I just go here and select this, what we will see is, in this model, we have augmented it with the profile that I mentioned earlier, which is this profile that augments the standard UML with needed information. And in this context, once the profile is added to this standard UML here, so this is usually done by selecting here, and you can just, typically you go select whatever profile and then you can add it. Once it's made available, it means that whatever the profile has built in, and in this context we've added some stereotypes which which provide some ASCETiC specific information, we can just go ahead and move to annotate any deployment diagram, so nodes of deployment diagrams with important ASCETiC information. So here in this context, by the way, let me first introduce what we're trying to attempt here. So we will deploy 4 different configuration of news assets. The first one, which will be where we have a load balancer HA proxy, which can redirect loads to news asset server, which operates the business logic of news asset. And then after that, it's these servers will then store the data provided by the user or queried by the user in the Oracle database, and like I said, the audio, videos, and image files will be stored in a separate VM yet here. So all of these boxes represent VMs, and each of these components are installed on separate VMs. Indeed, we are already even somehow having twice the same component here, the news asset server, deployed twice, so that we see if we drive higher workloads, we hope that these two servers will help. The second deployment is nearly the same. We have the HA proxy, except we only have one news asset server, so it could handle some load, but maybe less load. And then instead of deploying the Oracle and the file server in different VMs here, in this context, we deploy them on the same VM. The idea is, will it have an impact on response time? Will it have an impact on energy consumptions? For the same workloads that will be driven on each of these. Let's see. And now these two deployments are multi-tenant, okay, because they have this HA proxy sitting in front. But initially the way that news asset has been operating was not in a multi-tenant way, and so here we're also testing it in some of these other two deployments here, where we are packaging only the news asset server and the data server in a single VM. Here, and so here in these deployments, we will only have one VM which has the whole news asset system, the business logic as well as the data. And here it's the same one. The only difference between the two here is that the VMs are different. So this is a smaller VM, and this one will be a larger VM. The way this is controlled, by the way, the size of VM. So I will point out two things about rigid deployment that are important. Is how we can control the size of VMs. So if I select this VM, what you will see is all ASCETiC provided stereotype information here that would not be available in standard UML here. And so here, if I edit the VM characteristic here, what you will see is that for this VM, here are some typical numbers, so we can fix some number of CPUs, the frequency of the CPUs we want to have, and each time we fix a range, because this will then be negotiated by the PaaS, so it can find something in the 3 gigahertz range here. For the memory, RAM, we want 4 gigabytes of RAM, and for the disk size, we want something between 500 and 1000 gigabytes. And so here we can fix this. So if you look here in this VM, we are in the 3 gigabytes range. And in this other VM, we are in the 2 gigabytes range. Okay, so that's the only difference between these two deployments. Now, next to specifying the characteristics of VMs in rigid deployment, another very important aspect is how are we modeling which component gets installed where. And this is done through the cookbook here. So one aspect that we have discovered while discussing with typical DevOps is that it's very convenient for typical SaaS analysts to model their deployments with VMs like this, with a graphical, to just have a simple graphical way to express what's going on. But then in the end, in the background, the DevOps who actually perform the deployments, they often rely on configuration management technologies like Chef or Puppet. Here in the context of ASCETiC, we've covered the Chef case. And therefore, what we are providing here is for the DevOps to tell the analyst the set of cookbooks that should be installed on each VM. So here, for instance, there'll be a list of 3 cookbooks. And let's say the third cookbook here is a package that is stored here, and that will be during the deployment process, during the VM construction process, this package would be untarred and the Chef Cookbook inside will just be installed on this VM. And they'll be installed in a sequential manner. So this will be done first, and this second, and this one third. On all cookbook, we need to, here, since these are Windows VM, we need a Chef handler that is bootstrapping the process to make sure that Chef gets installed. Some other cookbook relate to configuring Windows as well for properly operating news assets, and then only after that we install the news assets. So we can decouple and have several cookbooks installed on any of these VM. So for instance, here we see that 3 cookbooks were installed. If I go to another deployment and if I pick here the data VM, what cookbooks are installed here? Well, we have 4 cookbooks. Okay, so here, I think we found it was a very convenient way for a dialogue between SaaS analysts and SaaS DevOps to operate. One had a simple, elegant way to just model deployments with simple little boxes. At the same time, it's convenient for the DevOps to keep their ways of doing deployments through Chef configuration. So now, once this is described, what we need to do is, for each of these deployments, we need to now generate an XML that will be passed to the application packager. And the way we generate this XML here, by the way, here are some old ones that I left dangling around. I will just remove them to show you. They actually get generated. So this top-level model here, this main model here, contains all the other models, so which contains where each is just one diagram. So what we will end up with here is, by calling the Axeleo plugin to it will traverse all of these different deployment diagrams and generate an XML for them. Okay, so, and this XML is somewhat a readable XML, and I will show you in a second. Hops, and you see here that this is regenerated. Some models were there. If I pick the second here that I'm on here, it has 3 VMs. This is this one, and I will open it with a text editor. And here it is. You will see the 3 nodes here. The 3 nodes which are now transforming the UML diagram into a simple XML that can be passed on, and later it will now be transformed into an OVF. What we can see is just packaging in a very simple textual fashion what was be specified graphically, so that a SaaS analyst doesn't have to remember all the details of this XML. Now, if they want to change a little something and they are expert enough, of course, they could just adapt this. For instance, if it's not on localhost and it's somewhere else now because they've changed it, and they've, instead of editing all their diagrams, they can eventually even directly do it in the XML if they prefer. Now, these XML files, they are understood by the application packager. The way you invoke the application packager is through this top menu here. So once we browse here, we can go ahead and select one of these XML files. But as I say that I'm covering, I won't go through the entire deployment process here, and so I've already browsed, so it's in this diagram. So if I pick the second one, which I'm showing you here in my editor, I can go on this, and the application packager is a simple wizard that gets the SaaS development team to deploy the application. So here first, it will generate. First, it shows exactly this. So it shows to the user the input that was open in my editor. Eventually, if something somehow went wrong in the generation process. Maybe this is empty or something else was wrong. At least they can verify this. Once they double check this and see that it's fit for continuing the deployment, they just go ahead and a first version on OVF is generated. We see that already this is going to be much longer, and the OVF is a bit less readable to the human and not so easy and fun to edit anymore. So this is why the application packager is very useful here when we see all these XML details that is covered here. The next step, which I will not cover, is the application packager passes information to the virtual image constructor. And the virtual image constructor, what it does, it actually builds the image, the VM image, and install the cookbooks that are mentioned. And then after the VM image constructor has cooked them and has built them and deploy them at the PaaS level, then it becomes the PaaS. The last step of the application package is to request from the PaaS layer to deploy these VMs at one particular IaaS provider. But that will be mentioned a bit further in the process. So once here now what I will do is I will jump from, let's assume that these 4 deployments have been pushed in ASCETiC Cloud, that ATC's team has driven all the workloads, and now what we will do is that the workloads, all the measurements have been taken by the ASCETiC Cloud, and that we have run the experiments to retrieve all of this and store them in the SaaS knowledge base. So now what I will do is I will go ahead and show you the visualization tool. I will go ahead and start from scratch, which we've already deployed internally at ASCETiC here. But so here, what it does, it's we have an experiment which consists of these 4 deployments that I've just mentioned, and we just go ahead. Here are the 4 deployments, so that we mentioned, and let's explore. And get a sense of how they perform in terms of cost, energy, and time by looking at some graphs here. So already here, we can already see some information here at the high level of what happened with my deployments for running all the workloads. And we already see that, for instance, the deployment here, 1018 and 1083, seem to be performing a lot better than the 22 and the 93, which use a lot more energy and cost a lot more. But we will then dig a bit in details of this. Okay, so here we can zoom in, zoom out if we want, but let's first look at all the data in a 2-dimensional way. These histograms are meant to filter sub-values, ranges, but before that, let's just go and check this 2-dimensional graph here that we have. So clearly we see that the 22 and the 93 that I mentioned, which are the little purple and green, we see that they spawn this way and they spawn that way, where we barely see the blue and the reds, who are probably somewhere here hidden and have performed a lot better. Some aspects which is important that we can also look at, we can play around with whatever measurements goes on the X and Y axis. So if instead of, let's say, energy, I want to look at duration here, we can just go ahead and play with them, and we see here that somehow there is a correlation between the costs and the duration, clearly. And again, we see that the 22 and the 22 in green and yellow are not performing well in terms of duration, and that's also why probably they cost a lot more and they use a lot more energy. In order to zoom out in one of the 2 that we prefer, let's unselect those that perform poorly, so the 93. and the 22. And now what you see is that this zoomed out. Oh yeah, well, maybe I should have highlighted this. Here what you see is that this is in milliseconds here, so we're talking about 600 seconds. This is a huge amount of time to run some of these workloads. Here we are looking at 508 seconds. Here at 600 seconds. When I unselect that, the graph will automatically zoom. And here now we see that the deployment 18 and 1083 here are performing a lot better. They are only 22 seconds for the same set of workloads, by the way. So these are the same set of workloads which you can see here, the list. So after some deeper analysis, looking back at what we were modeling previously, what we are discovering is that 18 is this deployment. 83 is this deployment. So this is not multi-tenant, while this one is. So clearly, when we were showing this information with and sharing this information with ATC, they were more interested to pursue with the multi-tenant one, so the 1018 here. And so if I just go ahead and show you the 1018 here, here is how it behaves in terms of the heavy workloads. Each time you see the name of the workloads here, the second line in the little hint box here is each time those are the heavy workloads where we are handling 100 concurrent requests being performed. The medium workloads are 50 requests being handled concurrently, and the lighter workloads group here that you can see is where we're handling only 10 concurrent requests being performed. What we can view as well here, it's the cost is very low. What we see in general, if we divide these workloads by the number of requests that are performed concurrently, here we see that it takes 5 seconds, so it's nearly 1 second server time to serve the requests. Here we are also, when we divide by 50 here, we're performing better actually, because if we divide, 15 seconds by 50, we're way below 1 second. And here again, if we divide by 100, we are also way below 1 second. We are around 0.2, 0.3 seconds per request. Here, a bit below 0.5. And here, if we divide by 10, which is the number of requests done by the light workloads, 5 seconds, that's nearly a second here. So this is to be kept in mind, because these will use when we specify our self-adaptation rules and our SLAs here. Once we've selected a deployment from these, from looking at the data, we will now move on to the second type of aspect of the demo here. And here what I will show you is how we can specify and augment the selected deployment and add SLA conditions to it, an adaptation rule, and this will be again added to the XML that I will show, and it will generate the OVF, the appropriate OVF afterwards. So let me move on really quickly here, not to go and spend too much time on this. This has already been partly done here. I believe that, unfortunately, okay, so, well, yeah, so in this case, I've should probably show you. Edit this one. I kept the two VMs separate, but indeed, it was a choice. We did discuss that with ATC, and the point was instead of stashing like the 18 where the Oracle DB and the file servers were on the same VM, they thought that it still would be nice to keep them separate just for backup reasons. So clearly it's not always, you see that, we can perform experiment as much as we want, but there might also be some other consideration to take into account in the end. So let's see here how we can augment our current deployments to make it self-adaptive. And so here, if I move to the profile and I look at the SLA condition and the VM adaptation, here it is. We have two types of adaptations rules that we have added to this VM. And this one here is a scaling adaptation. Let's edit it. I've already edited for us here. Oops, I need to select it first. And it specifies here that the event that is search for news item, so when people are performing requests which are searching for news item in the DB, we want the duration of this, so the metric which will be stored duration, which is a probe that's been designed by the news asset team, must stay under 0.7 thresholds that we've decided to see how it would operate with that. And now it's not that every single request needs to be under 0.7 seconds. Sometimes we tolerate a bit of a slowdown, but so that's why we perform some aggregation and we look at the number of searches that were done in the last 15 minutes, and we want the 90th percentile to be below 0.7. And so this is how we can specify such rule. And in case such rule is not met, then the self-adaptation, we want to tell the self-adaptation layer of the PaaS level that it should be able to perform some different scaling action. If the violation is not too important, what we will show is we want to do some vertical scalability. So maybe by increasing the number of CPUs, maybe, for instance, or increasing the RAM size for the VM. The other type of scalability is if we are violating this threshold of 0.7 seconds to much larger, so 50% or above, which means a bit more than a second, then we should do some horizontal scaling up. So now, all of that said, if I go ahead and go through the process of, again, generating the XML, we have the model XML, which is here. I had shown it to you already here. Here it is, and you see that it's a lot more complex than the previous one. It has some added SLA targets. It has some adaptation rule information that is specified here. And this will be processed by the application packager as well. So let's say here, let me now do one last thing for this demo here. So if I go to the base deployment, which is the name of, and pick this model, so this is the file that you see in the background that is shown here. We can trust that it is the same, and so on and so forth. So let me show you what the application packager does. And it generates this OVF. And if we look down in the OVF, but we won't necessarily have time to do that here at this point, what we will see is that it presents some of the information related to self-adaptation and to SLA in the OVF. They're all embedded in the OVF here. So here, for instance, you see some information about VMs. We also see some attributes, the cookbooks that need to be installed. All of that information will be used by the VMIC to construct the VMs, and then after that it will also be used by the PaaS layer to somehow monitor, use the SLA and the self-adaptation engine that are at the PaaS level to verify that SLA are met and to operate the self-adaptation. In this context, I will not go ahead and launch this because, again, it would take long minutes. It would take nearly, for building these 4 VMs, it usually takes around 4 or 5 minutes per VM to build, and sometimes even longer. So it will take us way beyond scope here. So what I just want to show here is that all of that information is now embedded related to the SLA and related to self-adaptation rules. They are all embedded in this OVF, and therefore, thanks to this, the SaaS layer can delegate the enactment of all the self-adaptation and verification of SLA to the PaaS layer, not worrying about it. And the actual results of the PaaS layer enacting these rules for SLA was actually already previously presented in a webinar that presented the PaaS level, and therefore we will not cover it here. So here, this is where my presentation will end, to show you what the SaaS level capability, the tools, the capabilities of SaaS level tools were in this context. Okay, so just as a quick reminder, we just showed you that the SaaS tooling, we're able to do some rigid deployment. At the same time, we can also augment these rigid deployment, make us self-adaptive by specifying SLA condition and self-adaptation rules. We also showed that there was a nice cooperation between this modeling tools and the application packagers and the VMIC to build VMs, although we have not actually fully built all these VMs. And then finally, I also presented that the Experiment Manager was a tool to be able to, once workloads were driven on deployment during development and test time, we could retrieve these measurements and present them in a graphically useful way to actually be able to select which deployment should be taken and how we should specify SLA rules and adaptation rules on certain metrics. And so this wraps up my talk.